Hello, everyone. What we're going to discuss in this lab theory lecture is how to use those tools that theoretically should have already reviewed in the other videos included in this Blackboard page. How do you use these tools? How do you choose the right tool with the final goal of performing any experiment with the highest accuracy possible within the limit of the experiment, and therefore produce the best results that you can get? So what we're going to talk about in these lectures are a few things. What are the important factors that affect your choice? Obviously, is the task. The first factor is, what are you doing? Does it imply a lot of accuracy, or do you have to go fast? How much inaccuracy can you tolerate? Obviously, the total volume of what you're measuring, your total mass, and then the availability of the tools is another limiting factor. Then we'll discuss very briefly, you see, it's very simple. How do you choose the right type of balance depending on the mass that you have to measure? And finally, we'll go through 4 examples so you get a sense of, within certain experiment, what would you choose? How would you choose the appropriate tools to practice basically these 3 main criteria of task, total volume, and availability. So as I said before, the 3 main criteria to choose the most appropriate tool in an experiment are the task. You obviously depends what you're doing. If you're preparing a solution, you will need to use the most accurate tool possible. If instead you're just transferring something, oftentimes in the lab, we don't want to contaminate the stock solution, what we call the stock solution. For example, if you have to take a reagent, you buy the reagent from a company, you don't want to take it directly from the bottle, the original bottle. You want to transfer a little bit, a little aliquot, as we say, into another container, and then from there you'll take the reagent that you need for your experiment. So if anything goes wrong, you do not contaminate the original bottle. So in that case, when you transfer it, you might not need to get the perfect volume. You might not require that. So you might use a different type of glassware that doesn't imply a super high accuracy. If you have to go fast, sometimes you have to trade some accuracy for speed. Maybe you're not going for the most accurate pipette. You might use another type of pipette, and we'll see an example later on. So the task is the first factor. Second important factor, obviously, is availability. If based on the task, you have to choose the most accurate tool that you get, but it's not available in the lab, then you have to settle for something, a second best choice. So availability, all labs are different. You see, availability affects your choice ultimately. And then obviously total mass and volume will dictate what is the best tool within those that you have available. So again, starting from the task, I'll repeat the same thing over and over until you remember that. The task is the most important thing. What does the task entail? Do you have to just quickly hold on to something? You just need roughly 50 milliliters that then you aliquot into other tubes. If it's roughly 50 milliliters, you don't need to use the most expensive, most accurate tool. You might pour it into a beaker, for example, which gives you a rough estimate of 50 milliliters. If you have to make a solution or a dilution, these usually imply a lot of accuracy. Then you go for the most accurate tool. A volumetric flask, for example. If you have to prepare a 100 milliliter solution or dilution, you will look for the 100 milliliter volumetric flask. Or if you have to go fast, you might use something that's accurate enough. Like I say, you have to deliver, you see later on the example, something in several test tubes. You don't want to do one measurement at a time for every test tubes. You might do one measurement and then use that one to basically deliver in all several test tubes. You see, so you trade a bit of accuracy for speed. Second issue is availability. You will see when you get to a lab that all labs do not have everything. Some labs may have more materials than others. So you have to work within the limitations of the lab. And so within the limitation in terms of glassware, pipettes, balances available there. So if you can't get the best theoretical option, then you look for the second best one. So for example, if you have to prepare a 100 milliliter dilution, and ideally you want to use the most accurate tool, which will be a volumetric flask with the same volume, 100 milliliters. But if it's not available, then you might have to settle for a second most accurate tool, which will be the graduated cylinder, even though it's not a two-contain tool. So you would choose a graduated cylinder if it's available with the same total volume that you have to prepare. Second, the last parameter that I want to discuss, at least in terms of liquid measurement, is the volume. You should always aim to use a piece of glassware or pipette which has the same total volume that you are trying to measure. So if you have to prepare a 100 milliliter solution, you look for a 100 milliliter volumetric flask. Or if it's not available, you try to use the piece of glassware that has the total volume as close as possible to the volume you want to measure. So for example, if you have to measure 90 milliliters, as you see in this example on the bottom, and there is no such a thing as a 90 milliliter volumetric flask in most labs. So, and what all you have available are these two graduated cylinders. Both of them would allow you to measure 90 milliliters. So it will be up to here in this graduated cylinder and up to here on this one. What you are trying to use is the one that has a total volume as close as possible to your 90 milliliter. So you would use the 100 milliliter graduated cylinder. This increases the accuracy of your overall measurements. Finally, and then that's pretty much almost everything I will say in terms of measuring mass. Is very straightforward, the rule that we use. When you measure a mass, let's say you're measuring to prepare a solution, you want to be as accurate as possible. And so in general, a generic rule is that the maximum error you can accept is 1%. You want to have a much lower than that, but 1% is the best or the worst error you can get when you do this measurement. So in general, the magic rule is if you have to measure something up to 1 gram, so or lower than 1 gram, you should use to get an error maximum to 1%, you should use analytical balance. Instead, if your mass is higher than 1 gram, like 1.2 grams, 2 grams, you could theoretically use also a top loading balance. I would still recommend that if you have a mass still close to 1 gram, let's say 1.2, 1.3, as I say, I would still recommend that you would use an analytical balance if it's available. Now, why? What base of this choice? As I said before, the acceptable, please take it with the benefit of the doubt what I'm saying, but the acceptable error is 1%. And to see how do you get there, we go through these two examples. So imagine you are asked to measure 0.1000 grams. You need that to prepare a certain solution. You want to be as accurate as possible. Now, if you used a top loading balance, since the top loading balance in the best case scenario gives you 2 decimals, 1 and 2 decimals here. So the best you can get to is to read is 0.10, right? Grams. In this case, that's the best you can get, the best reading that you can get. You think you're accurate, but in reality, you don't know what are going to be the next decimal, the third and fourth decimal here. So these values, since you don't see them, could be 0, 0, and that will be amazing because basically you're there, but you don't know if you're there. Or it could be 9, 9. So it could be 0.1099 grams. Now, if you do your calculation, you will see that in the worst case scenario, you could actually be introducing an error up to 9.9%. Extremely high error with this tiny mass. Instead, if you're using an analytical balance, obviously in this case, you can read up to the 4th decimal. So if you are extremely accurate, let's say you get the best case scenario is 0.1000 grams. Now, applying the same reasoning, you don't know what are the other decimals afterwards. So there can be anything from 0, 0. So you get to 0.1000 grams, this number right here, best case scenario possible. Or worst case scenario possible is 0.100, and these two additional decimal there will be 99 grams. But in this case, if you do your calculation, you will see that this error is 0.099%. So much smaller, 100 times smaller, not surprisingly, than the one you would get with a top-load imbalance. And therefore, this measurement, even in the worst-case scenario, will be the most accurate you can get between the top loading and then the analytical balance. That's the reason why you will use an analytical balance for this small mass. Now, if this was 1 gram, this error will go down by a factor of 10. So it will go down to 0.99%, which you can round up to almost 1%. So you start being within those reasonable limits of error, okay? Now, let's go, for example, to practice what we just discussed. So when it comes to measure volume, the three main criteria you use are the task. What does the task imply? Accuracy or speed, the availability, and the total volume. So let's go through the first example. So you're asked to prepare a 100 milliliter solution. And to prepare it, what you will need to do is measure the specific mass of the solute that is dissolved in the solution. We have not talked about solutions and dilution, but please trust me. You would have to measure a certain mass with the balance. So let's say you have to measure 0.6544 grams of solute. And you would have to resuspend it in 100 milliliters total solution, which would include the volume taken by this mass as well. So comes to the mass we just discussed, the best scenario in this case, since it's lower than 1 gram, would be to use an analytical balance. When it comes to the volume, then, what would be the best tool that you will use? We're talking about a solution, so you want to have the highest accuracy possible when you make them. So you might already introduce some error when you measure the mass. You want to keep adding error with your measurement. So you try to minimize the error as possible. So what will be the best tool to bring everything to 100 milliliters? Well, if you have reviewed the videos, you know that among the glassware or to contain glassware, the volumetric flasks are the most accurate one. So imagine this is your ability in the lab at this point. So you have a 100 milliliter volumetric flask, a 100 milliliter graduated cylinder, 100 milliliter beaker, 250 milliliters graduated cylinder, and a 100 milliliter Erlenmeyer flask. Now, as we said before, the most accurate option possible in this case is the volumetric flask. And you're in luck. This volumetric flask indeed allows you to measure 100 milliliters. They're a single volume measurement tools. So this one allows you to measure exactly this volume. So this will be your first choice. If this was not available, then your second best choice in terms of accuracy would be the graduated cylinder. And consider the total volume you have 100 milliliters. This will be your best option compared to the 250 milliliters graduated cylinder. If you are really bad luck, you don't even have that, oh my gosh, you gotta use a beaker, but that's the worst case scenario. You would never ever use a beaker or an Erlenmeyer flask to make a solution. It will be a huge error that get introduced there. Here you're talking about 5% error. So if you measure 100, it could be anything between 105 to 95 milliliters. So huge error they're adding there. Let's go through a second example. Now, in this case, you have to prepare 250 milliliters of a different type of solution, which is referred to as dilution. A dilution is a solution that is prepared starting from another solution, which is referred to as the stock or concentrated solution. This is with a high concentration. And when you prepare the dilution, so this second solution, you're lowering the concentration of the stock solution to a desired value. So in this case, let's say the final concentration has to be 50 times lower than what is referred to as the stock solution, the concentrated solution. So to achieve that concentration 50 times lower, if the total volume is 250 milliliters, you have to measure 5 liters of this stock and transfer it into 250, sorry, there's a mistake here. It's 250 milliliters total of solution. So this will be a 5, just to make sure. This is a 5, 250 milliliter total. I change it on the go. Okay, 250 milliliter total with 5 milliliters coming from the stock. So in this case too, this is a solution. The task already implies that you have to use the most accurate tool possible. So, and this implies for both when you measure the 5 milliliter of stock that you take from the stock solution, you transfer into this beaker, or this other container, and when you measure the 250 milliliters. So what is the most appropriate pipette you can use to take the 5 milliliters? Think about ideally. Pause the video and think what will be the most accurate pipette among those that were discussed in the other videos that you could use. If you have reviewed the videos, you know that what you will look for will be a volumetric pipette with a total volume of 5 milliliters. So a 5 milliliters volumetric pipette would be the ideal tool you could use if it's available. When it comes to 250 milliliters total, same thing. The most accurate tool to contain that you can use is a 250 milliliters volumetric flask in this case that you could use. So that's what you will be going to look for in the shelf in the lab. A 5 milliliter volumetric pipette and a 250 milliliters volumetric flask. Well, these are the pipettes you have in there. You're in luck. The 5 milliliter volumetric pipette is indeed available. So it's a no-brainer. You would take this pipette and you would do your measurement. This is, again, just reviewing, are a single measurement type of pipette. So you will bring the volume up to this mark in here, which corresponds to 5 milliliter. And then you would eject it into the other container where you would measure the 250. So what about measuring the 250 milliliters? Well, that's what you have available now. You have a 100 milliliter volumetric flask, a 500 milliliters graduated cylinder, a 250 milliliters beaker, a 250 milliliter graduated cylinder, and a 250 milliliters Erlenmeyer flask. What is your best option? Well, when you were thinking about to measure 250 earlier on, you were thinking, hopefully, to use a 250 milliliter volumetric flask, but clearly is not available. So even though the task implies to use a volumetric flask, now the availability limits the second best option, which are the graduated cylinders in terms of error. So again, total volume is the third criteria you use. 250 milliliters, try to use the tool with the same volume or closest volume. In this case, will be these graduated cylinder with a total volume of 250 milliliters. Not the ideal tool in any way, but the best one in this scenario, dictated by the availability. Example 3. In this case, what you're asked to do, and you do it all the time in the lab, is you got to set up 100 reactions. So you have 100 of these test tubes, imagine, and you have to add to this test tube all the reagents necessary to perform the reactions in all of them. When you do these things, usually you want to do it fast enough. Fast where the accuracy is still okay. It's not going to be the best accuracy, but it's not going to take you a full day just to set up these test tubes. You want to get the results within a few hours or even a few minutes. So you got to go fast. So let's assume that at the end, you've already added a lot of reagents here. At the end, you got to add 1 milliliter of the final reagent to these 100 test tubes. Now, since you got to do it fast enough, you have to find the right balance between accuracy and speed in this case. So you might not go for the most accurate tool. At the same time, you don't want to go for the least accurate tool. So what would be the best scenario here? Think about it. Ideally, you would want to use a 1 milliliter, volumetric pipette if you want it to be the most accurate possible. But again, 1 milliliter volumetric pipette in this case would take a long time. You would have to suck up the liquid in the pipette and deliver it for each test tube. So you would have to do that 100 times, not the fastest option. So Imagine this is your availability in this case, and you have that 1 milliliter volumetric pipette. As we said before, it would take a long time. It would be the most accurate tool to use, but every time you would have to suck the liquid up to the 1 milliliter marking, wherever it is, I can see here, and deliver it. Suck the liquid up, deliver it. Would take a long time if you have to do it 100 times. So in this case, then now imagine you have a 5 milliliter serological pipette, I believe. I see the markings well. Yeah, this is a serological, and this is a serological as well. I see a 9 there. So this is a serological. So you have a 5 milliliter serological pipette and a 10 milliliter serological pipette here. Which one would give you a good trade between speed and accuracy? Well, the 10 milliliter will be the best one to use. Why? And how would you use it? Basically, you would suck up the liquid all the way to 10 milliliters, and then you will go on top of each test tube and deliver 1 milliliter. So you will go from 10, so 0 to 1 in the first test tube, 1 to 2, second test tube, 2 to 3, and so on. By doing that, you will still be accurate enough, not the highest accuracy, but usually with this type of reaction, you repeat the experiment several times, which accounts for increased error. But so you would have to do this 10 times instead of doing 100 times with 1 milliliter. You will go much faster, and your timing will be now compatible with real life lab work. Okay, so sometimes you gotta trade if the task required to do so. Final example here is, in this case, you gotta prepare another dilution. This is a solution, okay, where you lower the concentration of a stock concentrated solution. So, and you have to reduce the concentration in the dilution of 100 times. So the total volume that you gotta prepare is 10 milliliters. So if you have to reduce the concentration by 100 times, what you gotta add from the stock solution, it's 100 of this volume, so it's 0.1 milliliter, which translates into 100 microliters. So you would take 0.1 milliliters of this stock solution, you would transfer to a container that allows you to measure 10 milliliters, and you will bring the volume to 10 milliliters. We'll talk about that when we do the dilution. Well, this, obviously, you gotta prepare a dilution, so which is a solution. You gotta be as accurate as possible. So now, just to go faster, let's assume that to measure the 10 milliliter, indeed you have a 10 milliliter volumetric flask. We already practiced that in previous examples. You got it in this case. You got the ideal tool there, the 10 milliliter volumetric flask. How about the 0.1 milliliters? What would you use? Imagine this is your availability here. You have a 1 milliliter serological pipette, which allows you to measure in 0.1. So each of these spacing here from a 0 to 0.1, 0.2, each of these spacing here will be 0.1 milliliter. So you can measure with this. Or in alternative, you have a series of micro pipettes. This one, the one with the blue cap or blue top button here, will allow you to measure between 100 to 100 microliters. This micropipette here, it says 100, so usually is from 1/10 of it, so 10, to the volume specified here. So from 10 to 100 microliters. And this one allows you to measure between 2 and 20 microliters. Which one will be the ideal tool? Well, in this case, you gotta have the highest accuracy possible, which you can't really achieve by measuring this spacing here in this serological pipette. The best tool will be micropipette. These are extremely accurate tool when they're used properly. Now, which one will be the best choice? Clearly, it's not the 2 to 20 microliters, because if you set it to 20 microliters, you would have to do this measurement 5 times. Every time you do a measurement, you introduce an error. So you would introduce 5 times the error. You want to do it in a single delivery. Now, this tool allows you to measure 100 microliters. This one, it's on the lowest end. This is on the maximum spectrum. As we say before, with the total volume, with the volume that you want to deliver, look for a tool that has a total volume identical or as close as possible to what you want to measure. So if you have to deliver 100 microliter, now you will use this one that has a total volume of 100 microliter. smallest error possible compared to this one where you will be in the lower end of the range that this micropipette allow you to measure. So resuming here, to measure this 0.1 milliliter or 100 microliters, at this point, you would choose this micropipette here, which allows you to measure exactly 100 microliters as a maximum total volume there. If it were, let's say, 200, at this point, you would not use this micropipette if you had to measure 200 microliters, because it would be out of the range of this micropipette. You never use this micropipette outside of the range. You would have used this one right here. All right. So I hope all these examples help you to visualize at least what you would do when you're setting up or planning an experiment, choosing the appropriate tools. So what we're discussing here, how do you choose the tool based on these three criteria? Task, accuracy. Do you need to be extremely accurate, or do you have to be fast, trading a little bit of the accuracy there? Or you don't need to even to be accurate. If you just have to take a piece of glassware and keep some sample there. For example, in this scenario here, if you have to set up this 100 reaction, so you will need roughly 100 milliliters here to transfer in this test tube. So you go to the original bottle of the reagent, and you would transfer roughly 100 milliliters into a beaker, right? The beaker has a 5% error. So even if you get a bit higher, 105, or you aim actually a little bit higher, even if you're higher than 100 milliliters, too bad. But at the same time, just transfer to the beaker so you don't go inside the stock bottle, the original bottle, with the risk of contaminating it. So you transfer into a beaker, the measurement is rough. You don't need to be accurate, right? And a beaker allows you to transfer this volume into this 100 test tube faster than if you use something with a small opening, such as graduated cylinder or a volumetric flask. So the beaker will be the ideal tool in this case. You don't need accuracy, you use that just to leave roughly 100 milliliters. So that's the task, the first criteria that we discussed here. Then the total volume. You always aim to choose a tool with a total volume identical or as close as possible to what you have to measure. And you want to reduce your measurement possibly to a single measurement. Sometimes you can't do that, but you want to reduce it to a single measurement. The reason being that every time you do a measurement, you introduce error due to your tendency to introduce error when you read something. You read a meniscus, something, you introduce an error. And then the availability, obviously, you are limited to the tools available in the lab. Then we discussed how do you measure masses, how you choose between a top loading balance versus an analytical balance with these cutoff, if you want, of 1 gram. Higher than 1 gram, it's okay to use a top loading balance. Lower than 1 gram, you will use an analytical balance. Again, I still stress, if you're close to 1 gram, a bit higher, 1.2, 1.5, if possible, still use the analytical balance. Okay, that's the best tool that you could always use if that's available. All right, that's the end of it. I'll post the assignment very soon.